It's always fun to be back here. This talk will have no equations. It will not use the letters G, R, M, H, and D together. When I was writing this title slide, I looked at whatever I emailed a couple of weeks ago as my title, discovered that it has 3 lines, and decided to abbreviate it to Rubin Rocks. This is a double entendre. This talk will be on LSST in general. I'll give you a little bit of a status update on Rubin Observatory and the LSST survey that is going to execute. And then I'll go in depth into one area for what we're going to be working on, the solar system, how we're going to map it with large surveys and clever software. So let's talk about Rubin first as an introduction. Rubin is a new special purpose observatory currently being built in the Chilean Andes. It's a survey telescope. It is being built specifically to conduct a comprehensive deep time domain survey of the sky called the LSST, or the Legacy Survey of Space and Time. Think of it as repeatedly imaging the visible sky down to about 24th magnitude in 6 bands over 10 years, resulting in roughly 60 petabytes of raw data. We're projecting we're going to identify an order of 40 billion stars, galaxies, and asteroids. So it's roughly 20 billion stars, 20 billion galaxies, and a little bit of asteroids. There are going to be repeated observations. So in total, by the end of the 10-year survey, think of a database with an order of 30 trillion observations, so 800 observations per object. As many of these big surveys, this has been going on for a while. I want to acknowledge this is currently the largest NSF and DOE ground-based astronomy project, but it wouldn't have gotten off the metaphorical ground without Kickstarter funding from Charles Simonyi and Bill Gates some 20 years ago that allowed us to de-risk the project and actually get the federal agencies to fund it. This is what Rubin looked like about a year ago. The building is nearly finished. Here's a person to give you a sense of the scale. You walk in, you are greeted by this huge telescope mount. This is an 8.4 meter telescope, 8.4 meter primary. It's very short and stout, and that allows it to move very, very rapidly. So this is not a time lapse, this is a real-time video. This is about 250 tons of steel and ultimately glass that can do a 180-degree circle and stop and be ready to take an observation in about 18 seconds. So I looked, and there was some debate on Twitter, but we decided that this beats the Cherenkov telescope array telescopes by about 2 seconds in how fast it can move around. Here is the glass blank back in 2008 when it came out of the oven. You see we were allowed to walk on it. Here it is in 2015 when the polishing was finished. You see no one was allowed to walk on it at that point. You can also tell that some of these folks look a bit older. And you're the first audience that sees this plot. I got approval to show it just this morning. The reflectivity of the mirror meets and exceeds requirements, so we're very, very happy with how that went. The mirror collects the photons. This camera identifies them. So this is the camera, or the camera detects them. This is the camera back in October of 2022 at SLAC. It's the size roughly of a small-ish jet engine. It definitely has that kind of a feel. 1.2 meter lens, 1.6 meter opening aperture. Here is one of the photos from a series that Avi showed. This is a pinhole image of Vera Rubin taken through the camera. If you go to this link down here, there's a really nice interactive viewer that you can use to zoom in and examine this image in its 3.2 gigapixel glory. Where is the camera right now? This is, again, from, I think, 3 days ago from from Slack. We're getting ready to move. That's the camera was being put together at Slack at Stanford. These are all the crates that are getting ready to be loaded onto a chartered 747. There's a lot to load, and it's very valuable. So it's getting the project is getting a plane to fly us directly there, and it'll be in Chile later this month. So once it gets there, this is an actual photo of the observatory and the 1 meter auxiliary telescope a little bit on the side. Once it gets there, we integrate everything, and then what you can expect is a commissioning camera. It's a smaller camera, only 5% of the large one. We're going to have what we call ComCam First Photon in August 2024. So in about 3 months, we see the sky for the first time. Then the large camera, LSST camera, we see the sky for the first time sometime in January of 25. And then the public first light image, so think press conferences, Joe Biden, maybe not, in April 2025. And then operations start in late 2025. So if there's one thing that you want to take away from this talk is that after 20 years of R&D and construction, we are now months away or a year away from actually getting data from this telescope. When I say we, I mean really all of us. What is the data we're going to be getting? How to think about LSST? So the telescope or the observatory itself is called the Rubin Observatory. The survey it's going to conduct is called the Legacy Survey of Space and Time. And the way I think about it is this is a telescope that will take roughly 500 pointings per night. And to each pointing, it will go back twice. So it'll take 2 visits. They're going to be about 20 minutes apart. Each visit, it takes 1 30-second exposure. That's about 10 square degrees. That's the field of view. It goes down to roughly R band of 24. There are 6 bands, U, G, R, I, Z, and Y. Take all this together, we're going to get about 4,000 unique square degrees surveyed per night. And then we repeat that for 3,300 nights for 10 years. This data set is going to allow us to look at a number of different themes. You've heard over the past 2 days about probing dark matter and dark energy, about mapping the Milky Way from Anna's talk and many others. This morning, we've heard more about the transient sky. And what I'm going to be focusing on here is the solar system to start this last part of this conference. When I mean the solar system, I mostly mean minor bodies. I mean asteroids, trans-Neptunian objects, and comets. We're going to be finding slews of these in the solar system. And what is an asteroid? It's, asteroid people are going to get mad at me, but big rocks, very big. This is a set of close-up images taken by spacecraft passing by asteroids. Here's another closer-up image, or up-closer image. This is from the DART probe, which impacted in 2022 the asteroid Dimorphos. This is what it looked like from Earth. See if you can tell what the moment of impact was. But from afar, this is how those asteroids look like. And this is usually a place in the talk where I ask the audience to point to the asteroid. Most people point to this one because it's in the center. But the answer is you can't really tell which one it is. You have to take multiple exposures to see if there's some motion. The only thing that's different about them in an astronomical image is whether they move or not. So the asteroid is actually this one here. And this is roughly how we identify them. Take a few exposures back to back. This is why LSST will be coming back twice to each pointing each night within 20 minutes to see whether anything has moved. And you get what is essentially a little vector. You know that you've seen something and you know roughly where it's moving. You do that tomorrow, you get another little vector that you could hopefully connect to the previous one. You repeat it again, and you have enough to solve for an orbit. And then you can project where this object is going to be going out in the future. So this is how we've been discovering asteroids for decades, and it seems relatively straightforward, except that when you start going very, very deep, you start going to 24th magnitude with a large field of view, this is what you see in every field close to the ecliptic. On thousands of objects, both asteroids, stars, false positive transients. And so these linkages that used to be easy to identify an object moving from just to image become ambiguous. There might be another detection over here that you might connect this object to. So you need to start thinking probabilistically about this and trying to figure out what are the all possible linkages in night 1 that you can link to night 2, link to night 3, link to night 4, and so on. And that makes the software, that makes the algorithm a lot more complex. Now, I'm not going to, well, first, the bottom line is we've solved this. I'm not going to go into detail how, but I will give you a sense of the big breakthroughs in this that allow us to do this kind of linking even when we have this density of objects. And the breakthrough actually comes from Matt Holman here. Matt in 2018 published a paper pointing out that one of the reasons why it's difficult to link these objects in the sky is that their trajectories are nonlinear. But the reason why their trajectories are nonlinear in the sky is because we're observing them from a moving platform that is the Earth. The asteroid moves, the Earth moves as well. So as you can tell, as the Earth moves, this asteroid is going to exhibit some kind of complex behavior. But if you happen to be situated in the sun, you take out the motion of the moving platform, and suddenly your asteroid starts moving in something that looks kind of like a straight line, and it's much easier to connect all of these things together. Now, you have a problem that to make this transformation, you actually need to know the distance to your asteroid, which you don't, but we can guess. And if we're wrong, we can guess again and guess again until we get something that looks like a line. So in a nutshell, this is the algorithm from Holman et al. Called HelioLink. How well does it work? Here's a whole bunch of asteroids in topocentric coordinates. That is what you would see on Earth. And this is what happens after you transform to a different system and propagate them to the same time. You'll notice that now all these little arrows are nicely clustered, and you run a clustering code over this and you find out which one is which. So we've implemented this at scale for Rubin. Ari Hines, research scientist at UW, is the primary author of these codes. And as of last week, on simulated data, we're getting 99.1% completeness. Ari was very mad that he couldn't get 0.2. For interstellar objects, we're getting, our requirements are about 95%. So all the numbers that I quote about predictions with discovery predictions assume 95%. So anything we can get above that is a bonus. And we're meeting all of them. And the really nice thing is that we think we can do all this processing on a smallish cluster. So our codes right now are actually clogging in at about 600 core hours per day needed. So we've got enough of a margin here for whatever reality throws at us. Speaking of reality, I tend not to trust simulations. I'm sorry, everyone, because they're usually too simple. Like anytime we would simulate data and then try to fit on that, the reality would surprise us. So it's really good to simulate, to test the codes both on simulations and on real data. So we did that using data acquired on DECAM. DECAM is also quite a sizable camera on the Blanco, and this code's already been finding asteroids over there. We also ran it on a survey called ATLAS, running out of IFA in Hawaii. John Tonry and company. And we managed to run it on their archive and actually find objects that were missed, because one of the things I didn't talk about is, but this code can find an object that's only visible twice a night. And usually today codes look for 3 or 4 observations per night. Atlas needs 4 observations per night to connect them. So we found a potentially hazardous asteroid last year, which was really nice to demonstrate that all of this will work for Rubin. And then once you find the first few observations, you can actually go back and find even more. So we found even more observations in ZTF. And then this object went from not being known to having a really well-determined orbit, and shown to the point that we know doesn't present any data to the Earth in a matter of hours. So to conclude this part, we have Rubin. It's almost done. We have the codes. They're almost done. We don't expect any surprises, famous last words. And now we're starting to think about, in addition to commissioning Rubin, can we do better? So how could we do better? Well, every time we search, the way we search for asteroids is we observe the same pointing twice a night to find two dots to construct a little vector so we can basically extrapolate those vectors. But mathematically, there's absolutely nothing from preventing you to solve an orbit if you only had a single observation per night with many observations over multiple nights. It's actually slightly better if you had observations spaced out further because it reduces your, basically shrinks the covariance matrix. The reason why we don't do this is just because we don't know which objects to try to connect. And so could we construct an algorithm that could do this, that could identify objects with just one observation per night and not two? And this is a talk on its own, so I'm just going to present the results. This was a PhD thesis from a couple of years ago by Joachim Moyens. The answer is yes. You can also do a clever transformation, something like, for those of you who have done shift and stack, like shift and stack in pointing space, a transformation of observations that turns observations that are generally nonlinear into lines in this transformed three-dimensional space, and then you apply a line-finding algorithm to it, something like a generalized Hough transform, and you can get them out. This requires lots of computing power. I should say that. There's no such thing as free lunch. That's what we're trading here. Does it work? We ran it on ZTF data. It recovered, we tried to recover known objects. It recovered about 95% of them, relative to just 44% that we get with kind of classical Helio-link type algorithms, or 66% by an algorithm that was developed specifically for ZTF. And the reason for this is that ZTF doesn't observe all its time in pairs. So that's why that's why these Helio-link type algorithms don't work that well. More interestingly, we then ran it on NORLab source catalog. NORLab source catalog takes all the images from DECAM, I think out to 2019, from the beginning to 2019. There's going to be a new update with recent data. 68 billion individual source measurements, roughly 1.7 billion that don't appear to be static objects. That could be asteroids or transients or whatnot. We ran on that and pulled out, this is about a year and a half ago, 1,200 known asteroids, and 104 new objects. This was just a test on 0.2% of the data to show that it works. And then this test enabled us to build a larger system because this requires more compute power. And just a couple of days ago, Joachim, who's now a research scientist and works with the Asteroid Institute, they've submitted to the MPC for verification about 27,000 new candidates identified from the NORLab source catalog. And this is with a scalable version of Thor now implemented on Google Cloud. For scale, typically worldwide, discovery rate today is about 25,000 new objects per year, and it will stay roughly that way until Rubin kicks in. And most of these asteroids are not really that unusual. They're main belters, but there are on the order of 100 NU candidates. So this is a nice kind of next step that I hope in a couple of years we'll be able to deploy to Rubin. And the nice thing about working in the solar system, I didn't realize that until fairly late, is that people understand what you do. And then they want to talk to you. So there was a lot of follow-up in the media, and Joachim picked up an IU prize for this algorithm. So what can we do with Thor-like algorithms? One of the things that we showed is that they allow us to search for archival data, but it also allows us to get better yields and cadence reoptimization for future services like Rubin. So if we don't have to come back every 20 minutes, if we can come back maybe every 2 or 3 hours, it may help transient science, it may help dark energy science, because they really want, they would love to have their uniform coverage of the sky and so on. So that's one example. Another example is we might be able to improve other missions like the NASA NEO Surveyor mission that currently I think is baselining something like 4 observations per droplet to find PAJs. A broader point is that this was purely software. And there's going to be some hardware. I guesstimated $5 million for LSST in terms of compute hardware that we need to run this. And if we could shorten the duration of LSST by only a year, let's say for finding the NEOs we'd like to find, that's the value of that is an order of 100 million. So you get with relatively small investments, you can get pretty high leverage on these size projects, which is why I think these things are quite interesting to study, these kinds of improvements. I'm going to just flash through this. This is my second question is, can we go deeper? So with algorithms like Thor, we can optimize the cadence, we can get better. Can we somehow go deeper than a single exposure on LSST? How would you do it? You would build coads. But how do you build coads for moving objects? Well, if you know how the object is moving, you shift every subsequent image to roughly where the object is supposed to be on the first image, and then you coad, and then you get increased signal to noise. So this is here us doing that for a fairly bright object, so nothing quite impressive here, but then look at an object that looks like this. So these are individual exposures for that object. So here's one where the weather was good, and you can sort of make out something, but this generally looks like noise. But if you know where that object is and shift all those images and stack them, you can get a significant detection. The problem is you generally don't know where those objects are. If you want to find new ones, what you do is you build these coads essentially along every plausible motion vector in the sky. So rather than build one coad, you go and build millions or billions. As you can imagine, that costs compute, but it's an operation that is incredibly well parallelizable, and GPUs are well suited for it. So this has been implemented in a piece of code called KBMod, which we're running now on DECCAM. Here's an example from a DECCAM survey called Deep. This is roughly a single exposure limit, and this is the exposure limit with shift and stack. It's about 2 magnitudes increase in depth. And we're hoping that we can get this to run on Rubin as well. So to start summarizing, we got a big telescope, we've got clever algorithms, and that will result in science opportunities. So let's look at some of those. I think this is the takeaway slide. These are the things that you want to be looking forward to in the next couple of years with Rubin if you're interested in the solar system. We're going to increase the number of known objects anywhere between factors of 5 to 30, depending on a population. And then these objects are going to be very well characterized. So you're not just going to get an orbit, but you're going to get an orbit, you're going to get light curves, absolute magnitude estimates, and a really well understood selection function. And I apologize for the colleagues in the field here who will notice that this column here is out of date because the world does move on, even as LSST takes time to build. But not by much. This is, I think, at 1.3 million right now. Peter will know. What can you do with this? Impacts on planetary defense. About 40% of objects that get close to Earth are currently known. These are the scary videos that work really well if you need to get funding from Congress. LSST can get that number up to about 70%, and then if we have more advanced software and some cadence changes, we could maybe even go as high as 85%. We can find temporally captured objects, these meter-sized bodies that come between us and the moon, hang around a bit, and then leave. Those can be used to study material properties, do in situ measurements and retrieval. There's this whole new space economy being built on resource extraction from asteroids. I always find it a little bit ironic that I'm showing this slide by a company called Planetary Resources that unfortunately went under. So that business is not quite there yet, but it will soon be, and we can provide it with targets. Going further out in the solar system, one of the questions that you may ask and try to get an answer on is where did volatiles come from into the inner solar system? We're going to map the main belt, see how many of those objects are active. Going into the Trojans, that's where we expect to find things that are very close to original planetesimals. We may be able to find objects for targets for extended mission for Lucy. Going further out into the trans-Neptunian region, objects that are dwarf planets like Pluto. This region in general gives us a sense about the history of the solar system and how the solar system evolved. We know that the planets have not started where they are right now. Exactly where they started and how they got there is encoded in where these objects are in the outer solar system. And we're going to get the numbers in that population up by at least a factor of 10, if not much more than that. Interstellar objects that Avi has already talked about. We know of 2 right now. With LSST, will go to anywhere between 1 per year to 1 per month, depending on how optimistic of a theorist you're talking to. I've turned full observer, so at this point, I don't care. I'll have the telescope next year, and I'll tell you the answer. And then Planet 9, and I think Konstantin is somewhere here. We have a debate in my group if Planet 9 is spelled N-I-N-E or N-E-I-N, and in German. Right? So we can never figure it out, but we're going to look for it, and Rubin should observe roughly 60% of the sky where it might be hiding, and indirectly set strong constraints if we don't see it directly. So my almost last slide. This is really the one to remember. Rubin is a 10-year mission, but a lot of these data for the solar system, the reason why I'm focused on the solar system right now, a lot of these data come in year 1. So this is year 1, we find almost half of everything, and then year 2, year 3, we get to 80%. So this is not something that you have to wait for a long time, but it starts next year. So over the next 5 years, we'll increase by roughly 5 to 30 times the number of known objects in every small body population in the solar system. The reason why we can get there is because we have larger telescopes and dramatic algorithm improvements. Simulations are there to get started. Ask me if you want to get a pointer to them. And on a personal note, after 10 years of working on LSST, it's really satisfying to see how all this is coming together. I left ITC in my last day was December 31st, 2011. I went to work for Rubin in Tucson headquarters because we were going to start in 2016. So took us a little bit longer than that, but it's here, and please use these data. Thank you very much.
Thank you, Mario. We have time for maybe 1 or 2 questions.
Quick question, you get it all the time, Starlink. What are you going to do about it?
So Starlink turns out isn't going to be that much of a problem for us. I think worst case scenario is about 1 to 2% of pixels get affected, but that's in the range of uncertainties about the weather. The dark energy folks are concerned because it might imprint directional patterns in the imaging that they otherwise wouldn't be there, and maybe manifest itself as shear. But it seems like it's all fixable in analysis. Still, it's good to be cautious because if no one said anything about Starlink, they wouldn't realize that they're actually potentially causing problems for astronomy. And it turned out after we started talking, they're quite a reasonable bunch. And like SpaceX has been really nice to work with to try to mitigate those effects as much as possible.
So you made a very convincing case that you've put a lot of thought into the software and it's optimized. Is the observing program optimized for solar system work?
So observing program has to serve a multitude of science areas. So it's a mix. We've had these, somebody said cadence wars, but then they said cadence diplomacy over the last 10 years or so. And it's not going to be ideal for any certain area, but the fun thing is when you build an ideal simulation, you get within 10 to 20 percentage points with the cadence that we've chosen. So things are, the fact that everything from dark energy to solar system can use the same telescope and get roughly 80% efficiency is quite amazing.
Thank you.
Okay, we need to move on, but let's thank Mario one more time.